In this video, we'll be continuing our investigation of sampling distributions. Here we're concentrating on specifically sample proportions. If you have not, this is part 2 of the video. If you have not viewed part 1, then pause this video and view part 1. Alright. To work the exercises we're going to have to work, we're going to need 3 rules. Rule number 1. Rule 1. The mean, mu, of our sample proportions, p hat, is going to be equal to the population proportion. This makes perfect sense. Our sampling distribution should be centered on the true proportion. If 30% of people have attended church in the last month, and if we do repeated samples and look at those p hats, it should be centered on 30%, if indeed that is true. Rule number 2. The standard deviation of these p hats, standard deviation of p hat, is going to be equal to the square root of the population proportion times 1 minus the population proportion divided by the sample size. So as our sample size gets greater, the spread of our distribution will be smaller. That makes perfect sense. All right. And as our proportion is closer to 0.5, then likewise that spread will be smaller. Okay. Lastly, rule number 3. This distribution will be approximately normal when 2 conditions are met. And those conditions are that n times p is greater than or equal to 10, and n times the complement, 1 minus p, is greater than or equal to 10. Alright, that is, the number of successes and failures must be greater than 10 in order for our sampling distribution of sample proportions to be approximately normal. Alright, let's look at how this directly applies to a couple of the problems they ask us to do. We're going to be doing page 372 and 373, 8.15 through 8.18, and we will work on these in class, and they won't be due until the following Thursday. That is Thursday the 23rd. So complete these examples here, and then I would hold the rest until class. So looking at 8.15, it says a random sample is to be selected that has a population proportion of p equals 0.65. Determine the mean and standard deviation of the sampling distribution of p for each of the following sample sizes. So 8.58a says that n equals 10. The question is, what is the mean of p hat, and what is the standard deviation of p hat? Well, the mean of p hat is equal to p, and they tell us in this situation for all of these it's 0.65. Alright, so whatever the population parameter is, it's happening 65% of the time. So that on all of A through F here, the mean of p hat will be 0.65. The standard deviation, by our rule 2 above, by this rule 2, it is the square root of p times 1 minus p divided by n. Alright, so in this particular case, we have n being 10. Thus, our p is 0.65. 0.65. 1 minus p, well, that's 0.35 divided by 10, and then we'll take the square root of that. So, using your calculator, perform that computation. and that is approximately 0.15. All right, and that's how you will handle all of 8.15. Okay, I'm going to go on and look at 8.16 now. 8.16. Says, for which of the sample sizes given in the previous exercise would you expect the sampling distribution of p hat to be normal? Okay, so by rule 3, we expect approximately normal sampling distributions when n times p is greater than or equal to 10, and 2, n times 1 minus p is greater than or equal to 10. Well, they want us to investigate for p equals 0.65 and for p equals 0.2. Well, for p equals 0.65, I'm going to look at n equals 10 for n equals 10, substituting into my formulas here. Thus, n is 10, my p is 0.65. Well, that is 6.5. And is that greater than or equal to 10? Question mark? No. Okay. Thus, for n equals 10, it is not. And you could progress in this fashion and check them all. Notice if you double this 20, you're going to have 13 there, and it will be. So for 20 and beyond that, it's going to. I'm going to show 20. For 20 times 0.65, well, that's equal to 13, and that is greater than 10. Yes. Okay. Now let's check the complement. 20 times 0.35, well, that's 7. That is not greater than 10. So no. Thus, 10 and 20 both will not. No. And no. All right. Once you get beyond 20 to 30, you're going to see it does satisfy. Looking at 30. Times 0.65. Well, you know, from 10 to 30, that's 3 times as much. So 6.5, 3 times as much, that's 19.5. 19.5, and that is greater than 10. Yes. Likewise, 30 times 0.35, well, that's going to be 10.5. And notice that these two numbers sum to 30 because this is my successes, these are the fails. Same way here, 13 and 7 sum to 20. All right, so both of these are greater than 10. So indeed, for 30, yes, the sampling distribution will be approximately normal. And thus it will be for everything larger than that. Okay, so for 50, 100, and 200. All right. So we've shown it for 30, then it will be for the rest. Thus, all n greater than 30 will also be approximately normal sampling distributions when P is equal to 0.65. All right, so if our probability is equal to 0.65, any sample of size 30 and above will have approximately normal sampling distributions. You should be able to have success on 8.15 through 8.18. Again, we will be working on these, working in class on 16 April, and they will be due the following, due 23rd of April. All right. Next, we need to look at the second section we're dealing with, which is 12. Next is sampling distribution. Sampling distributions of sample means. So previously we were looking at proportions, now means. All right. Like with the sample proportions, we're going to have a few rules. Rule number 1. The mean of our sample means, the mean of our x bars, will be equal to our population mean. Just like with the proportions, this is an analogous type situation. With our proportions, we had that the mean of our p hats was going to be equal to p. Okay. Here, the mean of our x bars is going to be equal to our mean. We expect that as we take these samples, they should be centered on the true population parameter. Rule 2. The standard deviation of x bar, I wrote this down here just so it wouldn't get cramped up with that one, is equal to our population standard deviation divided by the square root of n. And this is strictly saying we're going to decrease our standard deviation as our sample size increases. That makes perfect sense as before. Rule 3. If the population is normal, then the sample distribution will be normal as well. If the population distribution is normal, then the sampling distribution will be normal. For any sample size. The sample size being n. All right. And rule number 4, which is quite possibly the most significant result in statistics. It's sort of the link between probability and statistics, is called the central limit theorem. And the central limit theorem says, very large ideal in statistics, that when n is large, that's the sample size, n the sample size, the sampling distribution will approach normal regardless of the population distribution. And we're going to investigate this in class. Doesn't matter what the underlying distribution could be the craziest looking thing ever, but if you take a big enough sample size and look at the sampling distribution, it's going to be normal. And this normal sampling distribution will have the distribution that is listed in Rule 1 and Rule 2. It's going to be normally distributed with the mean, that is the population, and the standard deviation is going to be the standard deviation divided by the square root of n. So this is directly from Rule 1 and Rule 2. All right, let's look at an example problem or two. Okay. We are looking at page 492. We will be doing 12.1 through 12.5. Again, that's to be worked in class this coming Thursday. 12.1 says, a random sample is selected from a population with a mean 100 and a standard deviation 10. Determine the mean and standard deviation of the sampling distribution for each of the sample sizes. All right. So, using our Rule 1 and Rule 2, we want to find the mean of the sampling distribution and the standard deviation of the sampling distribution. So, for A, they give us that n is equal to 9. All right. And for all of these problems, we are given that the mean is 100 and the population standard deviation is 10. Okay, so we're just going to employ our Rule 1 and Rule 2. All right. Rule 1 says the mean of the sample means, is equal to the population mean. So in this case, in all of the ones, 12.1a and the rest of them, the mean is going to be 100. That is our population mean. The standard deviation of our x bars, our sample mean, is going to be our population standard deviation divided by the square root of n. So in this case, our population standard deviation is 10. Our sample size is 9. Thus, square root of 9 is 3. This is 10 over 3. That is our... So our sampling distribution is going to be centered on 100, and our standard deviation will be 10 divided by 3, which is 3.3 repeating. All right, you should be able to do A through the rest of them now. 12.2 says, for which of the sample sizes given in the previous exercise would it be reasonable to think that the x bar sampling distribution is approximately normal in shape? Well, 12.2, although this is a general rule of thumb, our book states, and this is not a written in stone thing, our book states the central limit theorem can be applied safely for n greater than 30, greater than or equal to 30. So we're going to go with that rule. The truth is it depends on our underlying distribution. If our underlying distribution is close to normal, it might take only a couple of a sample size of 2 or 4 maybe. But if our sampling distribution is extremely skewed, it might take more than 30. But let's go with what our book says and say greater than 30 here. Thus, for C, D, E, and F, okay, we can assume normality. Okay, because they all have greater than, all of these have greater than 30. All right, with that, you should be able to deal with the rest of those problems.